Hello and welcome back to the fourth and last lecture of Chapter 1. In this lecture, we're going to just finish up by looking at several other topics that are going to be important throughout the year. Most of these we'll come back to in later chapters and go through them in a little bit more detail. This will be just a brief introduction of the important things that you need to know right now. The first thing that we're going to talk about is how to add and subtract vectors. So a vector is any quantity that has a magnitude and a direction. A magnitude is just a number, an amount. So some things that are vectors include forces, velocity, acceleration, displacement. All those things have a direction associated with them. When we want to add up things that are vectors, unless they're in the exact same direction, you generally can't just add the two numbers together. There are a couple different methods that we can use. One of those is to add vectors using a graphical method. We'll learn some other more numerical methods a little bit later in the course. So if we want to add these two vectors, we have vector A, vector B. Vectors are represented by an arrow. The length of the arrow shows the magnitude, the direction of the arrow shows the direction. We're going to use a method called the tip-to-tail method of vector addition to add these two vectors together, to add any two vectors together. To do that, we first draw vector A, as you see here. And then from the tip of A, which is right here, we're going to draw vector B, like this. And then the sum, A plus B, is drawn all the way from the beginning of A to the end of B. It's going to look like this. One important thing to notice here is that B is always drawn at the end of A, what we call the tip, not back here at the beginning of A. Sometimes people want to always draw them coming from the same point. That's wrong. Draw A and then continue on with B wherever A ended. And then you go all the way from the beginning of A to the end of B. Now why don't you try it? Look at this question. We have P plus Q, and I want you to try to figure out what is the sum. What would you get if you added up P and Q? Feel free to pause the video for a minute and try to think about this and work it out, and then come back to find out the answer. Okay, were you able to decide that the answer was A? Then you're correct. Let's see why. Just like in the last example, we're going to find this resultant by adding these vectors together. We're first going to draw vector P, then from the end of vector P, I'm going to draw vector Q, right? So this is P, and this is Q. And then the sum, P plus Q, is going to be right here, which is the same direction and magnitude as vector A. Now, how would this change if we wanted to subtract vectors? Well, it's almost exactly the same. There aren't really many differences. If you want to subtract a vector, it's just like adding a negative vector. So if we wanted to say A minus B, what we would do is we would still start by drawing A, but when we get ready to draw B, instead of drawing B in the direction that it is, we would draw it in exactly the opposite direction, so the negative direction. So A minus B would still start here, but we'd draw B like this. And then once again, the resultant A minus B would be from the beginning of A all the way to the end of B. So let's go back and look at P and Q again. Now you try to subtract P and Q. P minus Q would be which of these choices? Once again, pause the video for a few minutes, work this out, and then come back when you have an answer. All right, is everyone ready? Did you choose D? That's correct. How do we know? Let's draw it out again. Start by drawing P. Now from the end of P, we're going to draw a negative Q. The resultant will be from the beginning of P to the end of Q, which is choice D. Now let's look at how to apply what we know about vectors to think about velocity and acceleration. We've already talked about displacement, which is a change in position, but it's also useful to consider a change in time. So an object, when it's moving, it moves over some time interval. Usually in physics, we're only concerned in changes in quantities. So the change in time is what's important. And this little symbol delta right here always is what we use to show that it's a change in something. So change in time here would be the final time minus the initial time. Two other new terms that we need to define here are speed and velocity. In everyday English language, these two words are used almost interchangeably. They mean exactly the same thing. But in physics, they have very, very specific meanings. Sometimes they're the same, but sometimes they're not. Their definitions are not exactly the same, and we have to be really careful about things like that. So, to find the average speed that something is moving, this is defined as the distance the object travels divided by the time that it spends traveling. So, distance divided by time. Importantly, average speed does not tell you anything about the direction of the motion. So, speed is not a vector. Remember, vectors are things that do have a direction. Also importantly, it's distance in the numerator. So distance and displacement are not necessarily the exact same thing. Remember that displacement we call delta R is equal to the final position of the object minus the initial position of the object. It doesn't take into account how it got between those 2 points. So, for example, if you just stood up right now where you are and you walked all the way around your room and you came back and sat down where you were right now, again, your displacement will be 0 because your final position, your initial position are the same. There's no difference between those. But the distance you traveled would not be 0 because you actually did walk all the way around the room. So, that when we're talking about speed, we're talking about distance, not displacement. Now, when we talk about velocity, that's where we're talking about displacement. So the average velocity of an object is the displacement of the object divided by the time. Speed and velocity might be the same, or might have the magnitude of the velocity might be the same as the speed if the object is moving in a straight line and it doesn't turn around, right? Because then distance and displacement would be the same. But in other situations where the object turns, where the object goes backwards, where they may not be the same, and then speed and velocity might not be the same either. So now that we know a little bit more about velocity, let's go back to the motion diagrams that we started this chapter with. Remember that a motion diagram is a way to show how an object's moving over time by representing it as little dots that are equally spaced apart. Well, we can add in velocity vectors between these dots. The length of the velocity, the magnitude of the velocity is proportional to the length of delta r, because remember that velocity is delta r over delta t. Delta t is the same for each one of these intervals. So we can label these here V0, V1, V2 for the 3 different velocities. Now we can tell by looking at this that this is going at a constant velocity for both the hare and the tortoise, and we can tell that the hare is going faster. We already know that about other from motion diagrams in the past. All we're doing here is adding in these velocity vectors. How would this change if you have something that is speeding up? Well, we can tell right here looking at this picture that this is a motion diagram of an object that is actually speeding up. All right, so we know that because each of these dots gets further and further apart, the velocity gets bigger and bigger as it goes up the hill. All right, so what this is illustrating is this is a motion diagram of a car accelerating from rest up a 20-degree incline hill. And we show the velocity vectors getting bigger and bigger as we go because the car is speeding up. When something's speed is changing, we say that it has an acceleration. Acceleration is formally defined as the change in velocity divided by the change in time. So it's the rate of change of velocity. It's how quickly the velocity is changing. So to find acceleration, we need to know the change in velocity. Remember, the symbol delta represents the change in something. So that's the final velocity minus the initial velocity divided by the change in time. So it doesn't matter how fast you're going. It matters how quickly your velocity is changing. So an object could be going really fast and have no acceleration. Imagine if you're in your car and you're going 80 miles an hour down the highway. As long as you're going at a constant 80 miles an hour, your acceleration is 0. But now say you have to stop your car at a red light, and then the red light turns green, you floor it and take off. Well, then you have a small velocity to start with, actually 0. You're stopped at the light. But your acceleration is really big because you're changing your velocity really quickly. Be really careful with these words. Velocity and acceleration are two things that students often get mixed up. You want to think that if velocity is 0, acceleration is 0. Not necessarily true. Or if there's a big velocity, there's a big acceleration. Definitely not necessarily true. So they're not the same thing. Acceleration measures the change in velocity over the change in time. It's a rate, how quickly the velocity is changing. So let's see if we can add in now an acceleration vector to our motion diagram, because the acceleration vector will tell us something about how the velocity is changing. So if acceleration is proportional to change in velocity over change in time, the direction of the acceleration vector is going to be the same direction as the change in velocity. So what we need to do is we need to subtract these vectors, just like we learned how to do a few minutes ago. We want to subtract to find delta V, the final velocity minus the initial. Remember how we did that. We draw the final velocity vector. From the end of that final velocity vector, we draw the initial velocity. Since these are lined up, you can draw it kind of right next to it so that you'll be able to see it. And then that means that the sum will go from the beginning of your first vector, which was VF, to the end of the second vector, which was minus VI. So this right here is going to give you the direction of the acceleration vector. On our motion diagram, what we do is we just draw the acceleration vector off to the side, so we show the direction. So if we redraw the motion diagram, it would look something like this. We would have the two velocity vectors getting longer and the acceleration in that same direction. Notice here that the acceleration is in the same direction as the velocity. That's something important to notice, because it tells you something about the motion of the object. Whenever you see that the acceleration and the velocity are in the same direction, then that means your object is speeding up. Now let's look at another example. Say you have an initial velocity, v1, given by the arrow here, and an acceleration that points upward. What would the second velocity vector that we would draw on this motion diagram look like? Well, if the acceleration is pointing upward, that means that the second velocity vector must be shorter than the first, because the velocity and acceleration here are in opposite directions, meaning that the object is slowing down. So if the second vector is shorter than the first, right, it's still going to be pointing down, but it's going to be a lot shorter. So the next one is going to be this one. What if you had an acceleration vector going down? Then it would be this one, all right, A, because then it would be accelerating, would be getting faster. So it would be becoming a bigger velocity in that same direction. So let's try to put all this together. Really, the overall goal of this whole chapter is to allow you to visually represent what's happening in a problem on a motion diagram. We started with just the dots. We added the velocity vectors. Now we've come back and we've added the acceleration vectors. We've put numbers on that, so we've gotten a complete picture of what's going on in the problem. So a complete motion diagram consists of all of these things. You need the positions shown by dots, you need the velocity vectors, and then you need the acceleration vectors. If there's no acceleration, you can just write A equals 0 so that you know that it's a constant velocity. So let's look at putting all this together. So you have a problem where it says a skier glides down along smooth horizontal snow at a constant speed, and then she speeds up as she goes down the hill. Draw the motion diagram. So we're going to start by drawing the dots. We start with putting these dots here in this first part. We draw the dots equally spaced apart because she's going at a constant speed. In the second part, we start to draw the dots further apart because she's speeding up. So here, there's no acceleration, right? So we write 0 here and here to show that we don't have any acceleration because the velocity vectors are the same length every time. It's constant speed. Then as it starts speeding up, the acceleration should be in the same direction as the velocity, indicating that it's speeding up. So we've been talking about this a little bit, but let's summarize what we know about these directions of velocity and acceleration. So whenever an object is speeding up, the acceleration and velocity vectors will always point in the same direction. Whenever an object is slowing down, the acceleration and velocity vectors point in opposite directions. So just because something has a positive acceleration doesn't necessarily mean it's speeding up. It's another thing that people usually think, but it's not always true. If it has a positive velocity and a positive acceleration, it's speeding up. But you could have a negative acceleration and still be speeding up if you also had a negative velocity. That would be like if you're in your car and you are backing out of a parking space. You may start from rest and you speed up as you go backwards. So you're still speeding up, but you're moving in a negative direction. If an object, on the other hand, is slowing down, then the acceleration and velocity vectors will point in opposite directions. Positive acceleration can also mean slowing down. So if you're moving in a negative direction, but you have a positive acceleration, then you would have a negative velocity, a positive acceleration. That would be opposite directions. You'd be slowing down. If acceleration is 0, it doesn't mean that the object is not moving. It just means that its velocity is constant. So looking at these two motion diagrams, both of these have a positive acceleration, right? But one is speeding up and one is slowing down. The first one is speeding up because the velocity is also going in a positive direction. So velocity and acceleration are both positive. They're both in the same direction, so it's speeding up. Here we have a positive acceleration, but we have a negative velocity. So if they're in opposite directions, it's slowing down. That's something to work really hard at remembering. So let's see if we can put all this together. A cyclist riding at 20 miles per hour sees a stop sign and actually comes to a complete stop in 4 seconds. Then in 6 seconds, he returns to a speed of 15 miles per hour. Which of these motion diagrams is going to correspond to this problem statement? Pause the video if you need to for a few minutes, figure it out, and then come back. Okay, did you get it? Let's see what the correct answer is. There's a couple things to notice here. First of all, notice that his initial velocity of 20 miles per hour is bigger than his final velocity of 15 miles per hour. So we can rule out some answers right there, right? We want to look for a motion diagram where the first velocity vector is bigger than the last velocity vector. So if we look at A, is this first one bigger than the last one? Yeah, it is. So that could be right so far. B, the first one bigger than the last one? Yes, it is. Look at C. The first one here is smaller than this one here. So this cannot be correct because it does not match that pattern. So we've ruled out C already. Now we can look at D. Is the first one bigger than the last one? It is. So we've still got A, B, and D as possibilities. The next thing to look at are the acceleration vectors. Now, in this first part, the velocity is getting shorter. It's slowing down. What direction should the acceleration vectors point? The object is slowing down. If these arrows are getting shorter, then the acceleration vector should point in the opposite direction to the velocity. So if velocity is going this way and it's slowing down, acceleration needs to be going this way. Which of these pictures has acceleration going that way in the first part? Not A, right? And not D. So the only possible answer choice here is B. So from the beginning up until this point when it stops, you have a positive velocity and negative acceleration. It's slowing down. Then it starts to speed up. Now the arrows get bigger, the green arrows, so we also have a positive acceleration. So let's put all that together and summarize everything we've said about these directions and whether they're positive or negative. This is a really tricky thing, and it's something we'll continue to practice in class over the next few days. Positive positions are determined by just literally where the object is relative to the origin. So if it's to the right of the origin, it's a positive position. If it's to the left of the origin, it's a negative position. If the object is moving to the right, then the velocity is positive. If it's moving to the left, its velocity is negative. Acceleration is a little more tricky, right? You have to think about how it combines with the velocity and whether it's speeding up or slowing down. So acceleration, Usually acceleration to the right is considered a positive acceleration, to the left is considered a negative acceleration. But we can't say anything about whether that means it's speeding up or slowing down without also knowing something about the velocity. So again, if we did this in the y direction, then we could look and say above 0 is positive position, below 0 is negative position. Up is positive velocity, down is negative velocity. And the same thing as before for acceleration. It can be positive or negative, but you have to look at it combined with the velocity to know whether that means an object is speeding up or slowing down. So in summary, the sign of the position tells us where the object is. The sign of the velocity tells us which direction it's moving, but the sign of the acceleration only tells you which way the acceleration vector. It doesn't tell you whether it's speeding up or slowing down. You have to look at acceleration and velocity together in order to determine that. Another quick question to apply what we're learning. A ball is tossed straight up in the air. At the very highest point, right where it turns around, what's the ball's acceleration vector? I'm not going to answer this question for you right now. I want you to think about it, and we'll talk about it at the beginning of class. One more question to think about. The motion diagram here shows a particle that's slowing down. The sign of the position and the sign of the velocity are which of these combinations? Once again, I want you to think about this, answer this question, and bring it with you to class tomorrow. And one final question. Same picture, but now, what direction is the acceleration? So answer these 3 questions. At the very beginning of class, we will discuss them. I'll see you tomorrow.